Hi, Kevin.
Hey, Dr. Wheeler. Did you check out Guillermo's video that he shared?
Yeah. Hey, guys. Hey, Lyle. Alex, letting people in here. Let's see. I didn't get a chance to check it out.
Yeah, it took up my whole hour. It was pretty cool.
Oh, really? All right. Well, yeah, I've got to go back and pick it off of our Zoom, but yeah, I'll post that link.
Yeah, I'm sure it'll be easy to find.
Yeah, that should still be there. Or yeah, I can find it. So yeah, what does it show? Is it like scattering off a barrier and double well and stuff like that?
It does a variety of potentials. It does like a ramp potential and infinite square weld.
Nice.
I don't think it did the double L. I can't actually remember. I think it did a total like 4 different setups.
Yeah. Once you've built the computer model of the superposition,
yeah,
that you can time evolve in a general potential, then you can do everything. Yeah, that's great. There have to be lots of things of that sort online at this point.
Maybe or maybe not, but that kind of remarkable.
Yeah, it takes some programming to actually get to move a Gaussian around, but I'd be surprised if it hasn't been done a few times. So let's see. You're muted again, Alex.
It's okay. I'm still blown away by that video too. I think it's so cool.
Oh, okay. All right. Okay, here comes Guillermo.
Our hero.
Yes. Good job with that video, Guillermo. I haven't had a chance to look at it myself, but I'm hearing great things about it. So thanks for digging that up. It's pretty amazing to see real wave packets evolve through various barriers and things, whatever. Okay, so today I want to talk about spin groups. So I guess I need to ask first what you guys know about it. Have you seen details of the relationship between SU2 and SO3? Or do you want to see details of that? That's the simplest case. So if that's not just totally familiar, let's do it.
I just say yes and yes.
Okay. All right. So I have to make sure I'm not stepping on a cat here. The idea of representations of Lie groups. Are you familiar with that? Is that something that I should say something about or not? I guess I'll say a little bit about it.
Yeah, we saw representations of the SU2 group when we were talking about the Dirac field and classical field theory.
Yeah. Okay. Well, we'll talk about representations. They're important because in some sense you'd like to have a handle on the different representations. One thing that I've got coming up in these notes is a calculation of all linear representations of the rotation group, and that underlies what we do in field theory and why we do it. So we'd like to get to that, but let's see, representations. Okay, so here's a simple example of representations. If I look at the numbers 0 and 1, addition mod 2, so that if you reach 2, you go back to 0, right? So if I add these mod 2, I'm adding 0 to 0 or 1. So 0 is acting like the identity here. And then 1 plus 1 is 2. 2 mod 2 is back to 0. So this is a multiplication table for a 2-element group. All right, where multiplication is used in the broadest sense. But you know, I can also write 1 and minus 1 under ordinary multiplication. And here, of course, I get 1 and minus 1, and going the other direction, I get 1 and minus 1. Minus 1 times minus 1 is 1. That is a different representation of the same group. And a more abstract representation, I can have an identity and one other element. The identity is going to give the same things on either side. And there's some abstract operation here that I'm performing, but A has to have an inverse, so I've got to have an E here. That's the same group as these two. These are 3 different representations of the same group. And basically, you know, as long as it's got the same multiplication table, it's the same group. Well, Lie groups have uncountably infinite numbers of elements, but we can have different representations for the same group. I'll give you a really trivial example. Suppose we have a 17 by 17 matrix, and in this corner I put a 3 by 3 element of the 3-dimensional rotation group, and then I put, you know, 14 ones down the diagonal. Well, that's a representation of the rotation group. It's an utterly trivial one, but it is a representation. There are much less trivial ones, and as we'll see. Now, the idea of a linear representation. A linear representation of a, let's pretty much stick to Lie groups. Of a Lie group is a vector space that the group acts on. And you know examples of this. We can write rotations as certain 3 by 3 matrices filled with sines and cosines and stuff. And we can accomplish a general rotation using Euler angles. So, an angle, you rotate around the y-axis by one angle, and then like around the new z-axis by another angle, and then another one, I think, around the new y-axis, something like that, Euler angles, the 3 angles that allow you to specify any rotation. We can also come up with a representation by exponentiating anti-symmetric matrices. This is a convenient one for SO3. So rotating 3-dimensional vectors. If I define 3 matrices, 0, 0.
Could you turn the screen down, please?
Oh, yeah, sorry. There we go. Let's try -1, 1, 0, 0, 0. Have to think. Well, either this or minus this. So just three matrices, 0, 0, 1, 0, 0, 0, -1, 0, 0. Let's see. All right, this should be 1, 2, row 1, column 2. Let me think here. 2, 1. Okay, 2, 3. Row 2, column 3 should be +1. Okay, let's do it this way. -1, +1, and 0, 1, 0, -1, 0. So this is a basis for anti-symmetric 3 by 3 matrices. Now, we can talk a bit about Lie groups. You have plenty of notes on Lie groups, but if you've seen a bit, you'll remember that by exponentiating an element of the Lie algebra, you get an element of the Lie group. So a general element of the Lie algebra is a linear combination of any basis. And if I exponentiate that, that's a three real parameter representation of the rotation group. Have you guys seen this? Is this new, or you're all right?
Yeah, some of us took Lie algebra from Dr. Fells a couple of semesters ago.
My Gatebury book has a couple early chapters on this kind of material. We can go back and cover this if you want. I want to make some different points today, but if I look at an infinitesimal version of this and demand that it be an infinitesimal rotation, I find that what works is any antisymmetric matrix. Basically, that'll preserve the Euclidean 3 metric. And so then I can do many infinitesimal rotations, and that always generates an exponential. So a general element of the rotation group looks like this, but what I can do is write that vector W as an amplitude and times a unit vector dotted with these 3 matrices. And this is some 3 by 3 matrix, and you can go through a detailed expansion of what this looks like, and it's all full of sines and cosines and stuff. You can actually look at the geometry and see that this describes a rotation about the axis n through an angle theta. So here we have one representation of the rotation group that is described by the 3 Euler angles. We have another representation that is described by the axis and the angle of rotation, which is, you know, a lot more intuitive to work with. So different representations for the same group. Now, this representation acts on real 3-dimensional vectors. So I take an x, y, z, and this is going to give me what that x, y, z turns into if I rotate it about a unit direction n by an angle theta. Notice there are still 3 parameters here. There are 3 Euler angles. Well, to specify a unit vector direction, I need, you know, theta and phi, basically. I need 2 angles. And then I've got a third angle, the angle of rotation here. I should choose psi or some different name for that. But there are 3 real parameters that describe any rotation. It's a 3-dimensional Lie group. So, oh boy. And I'm beginning to wonder whether I should tell you some of the basics of how I get this. Getting infinitesimal generators. Do you want to see that? Or should we go right to SU2?
I think we've already seen this in CFT, but I'm okay if anyone wants to see it again.
Okay, yeah, let's let me just review some properties of this without doing the whole thing. If I let theta be infinitesimal, I can write this as the identity plus theta n dot j. Or in general, let's see, I can, if I'm starting from a group with some number of real parameters, then I can take those parameters small. Now, I want a linear representation of the group. So let's see, yeah, all right, let's take those small parameters. A linear representation, there has to be an identity, so I can expand near the identity epsilon dot some matrices, linear combination of some matrices. If this is a rotation group, property of the rotation group is that it preserves the metric. So G eta G inverse has to give me the metric back. Euclidean 3 space, that's just the identity matrix. So GG inverse is 1. Let's see, that's not quite right. for that we need the transpose. What am I doing? G dagger. Oh, yeah, it's the transpose. I want the transpose for one of these. Yeah, let's take that one for the transpose. That's what preserves our inner product. And if this is Euclidean, then G transpose has to be G inverse, and that defines the orthogonal group. But if I expand as 1 plus some small matrix like this and impose this condition, then I have 1 plus epsilon times basically the Euclidean metric, which looks just like the Euclidean identity. And then the transpose is 1 plus epsilon transpose, and that's got to give me delta again. And if I expand this to first order, I get delta plus epsilon delta plus delta epsilon plus epsilon transpose. That's second order, is delta. And since this is just the identity, sorry, that's transpose, I see that epsilon plus epsilon transpose has to be 0. And so in order to build so any antisymmetric matrix will give me an infinitesimal rotation. So what I do is I choose a basis for all antisymmetric matrices. This is clearly one. Any linear combination of these will give me an antisymmetric matrix. So all things satisfying this condition are linear combinations of those. Then, to find a finite rotation, G of some finite W, what I can do is take an infinitesimal linear combination of these to the nth power, and I take the limit as n goes to infinity and n epsilon goes to some finite vector W. Can you see, am I writing big enough? Can you see that? You're okay? All right, so it turns out this is an exponential. You do a binomial expansion, you get binomial coefficients, you form n epsilon combinations, and that it gives you something that in the limit as n goes to infinity becomes an exponential. Have you guys seen that? Yeah, okay. Right, it's in the notes, it's in the gauge theory notes. So, you know, it's just a short calculation. It's not long, but it's not where I wanted to head today. So that's just the exponential of W dot J. I promise you, you know, check the proof. Okay, so from the infinitesimal generators, a basis for my infinitesimal generators, I take all linear combinations, exponentiate them, and I get general elements of the Lie group. This is actually the covering group. There's not quite a one-to-one correspondence, because if I take a quotient of this group by any discrete subgroup, I get something that's got the same Lie algebra. So Lie algebras and Lie groups aren't quite one-to-one, but they're one-to-one with these covering groups that you get this way. Okay, so this is a linear representation of a Lie group. And these J's, it turns out, satisfy properties. And so I've just argued that from the J's, I can get back to the whole group. So now what I can claim is that the essential properties of these J's actually determine the essential properties of the whole group. And the essential properties turn out to amount to 3 things. So a Lie algebra has commutation relations. So if I compute the commutators of any two of these, it turns out I'm going to get, now if I scale them right, I'm going to get epsilon ijk times jk. These are the fundamental commutators of the rotation group, and every linear representation of the rotation group will have a Lie algebra that looks like this, or can be put in this form. So you actually, just working with the commutators of the Lie algebra, you can find all representations of a group. All simple representations, I should say. There, you can add a bunch of identities. There's a rigorous sense in which we're not really interested in those. So this is one. Then we need the Jacobi identity, which says that if I take two of these and commute with the commutator of two more, and add the two cyclic permutations of that, I get 0. It's a little bit like associativity, but a little bit weaker. And 3, it's a vector space. So I can take all linear combinations of these basis things. And the group then is basically the exponential of that vector space. Exponentiate any vector in the Lie algebra, and I get a group element. Oh, this is yeah, I thought you guys knew this, but okay, Kevin, yes, question.
So that vector space, must it be finite dimensional?
Yeah. There are such things as infinite dimensional, things like Lie groups, but they've got a little bit different properties. So we're interested in finite dimensional Lie groups here. Like rotations of real 3 vectors, for example. Okay, are there other questions? I don't want to have zipped through too fast on something you guys really haven't seen before, but what I want to do is find a more basic representation for these same transformations. I want to find a representation by a spinor representation is what I'm after. Now, to do that, we can go one of 2 possible ways. One way just relies on the definition of a rotation, a real rotation, and that's probably the simplest thing. So these properties define a Lie algebra. If I have something with these 3 properties, the exponential of it will give me a Lie group. Let's consider matrices of this form. I'm going to call this a capital X. And I want to take linear combinations of the Pauli matrices. So this will take the form, we'll have Z and minus Z on sigma 3. I'll have X and X here on sigma 2, and then IY and minus IY on sigma 2. Sigma 1 is the XX. Okay, so you can see that this linear combination will give me a matrix of that form, and this is almost the most this matrix, as it happens, is Hermitian. The Pauli matrices are Hermitian. As an exercise, I don't know if I left this as an exercise, but show that linear combinations of the identity and the Pauli matrices give you the most general 2x2 Hermitian matrices. That's just that's a useful result. Or do it the other way. Write a general 2x2 complex matrix and show that if it is Hermitian, it can be written as a linear combination of these. It's maybe easier to go that way, but do that as a problem. An exercise, it's not too hard. Okay, so now this matrix X has some obvious properties. It's Hermitian. And the thing that keeps it from being totally generally Hermitian is we don't have the identity. All of these polymatrices are traceless, so trace X equals 0. Let's see. Anything else? Well, no, that pretty much characterizes. If you take any traceless Hermitian matrix, you can put it in that form.
There's no normalization condition.
Well, X, Y, and Z are arbitrary numbers, arbitrary real numbers. So you could fold a normalization into that. Yeah, so yeah, all that we're missing is the identity, and that's handled by the traceless condition. Now, let's look at the determinant of X. Okay, so we get minus Z squared minus the product of two complex numbers, so minus X squared minus Y squared. So this is minus basically the Euclidean length squared. Well, that's a cool thing. Okay, so here's a cooler thing. Suppose I write a transformation. If I take any matrix A, take its dagger, take X, and take A again. If X is Hermitian, then this is Hermitian, right? Because you flip the order and dagger everything, and X dagger is itself. So this will be Hermitian. Now, if I choose A to make this new, let's call this a new X. So I require trace X tilde equals 0. Now that's a constraint on A because X is already traceless. That's already fixed. We're given capital X. Then I require that, and I require det X tilde equal det X. Well, that's easy because that says the determinant of A dagger X A has to be the determinant of X. Now, the cyclic property of the trace. If I have a trace of a product of several matrices, I can move the end one to the beginning. And it's the same trace. So I can move this A around to the front and write this as the determinant of A dagger X. And so if A dagger equals A inverse, then that's just 1, and then that gives me det X. So the determinant of X tilde is equal to the determinant of X if A dagger equals A inverse. What's that condition called? It sounds off, Eli. You said unitarity, didn't you?
Yeah.
Okay, thanks. Okay, so this means it's unitary. So I consider unitary A, and what else do I need? Let's look at the infinitesimal case. If I let A be the identity plus something, alpha, beta, mu, nu, then let's see, what do I need here? Gosh, let's see. How do I do this? I suddenly forgot what I'm doing. Let's see. Okay, first I want hermeticity. Let's do it this way. So if I start with 4 complex numbers and I require that to be equal to a dagger, I'm going to get a real thing here, a real thing there, and some complex number here and its conjugate there. All right, to be Hermitian, it's got to look like that. And now, if I take, let's see, yeah, it's always annoying to have to figure out the trace condition here. It's oh, okay. So now let's just do it. Oh, wait a second. No, this is okay because the trace. Yeah, you guys should have caught me here. Okay, a determinant of a product. This is true for the trace, right? For tracelessness, unitarity is going to do it. The determinant, I do need to preserve the determinant, but okay, the determinant of x tilde is the determinant of a dagger x a. I need the determinant of x tilde to equal the determinant of x. But this is the determinant of a magnitude times det x. So what I need is the determinant of a has to be e to the I phi. Right? It's got to be just a phase. Okay. Yeah, that was the trace argument I did down here. Let me get back to that. So the phase, the determinant of a has to be a phase, but I can write a as a phase, probably over 2 times some transformation where the determinant of u is 1, and the determinant of this is then going to be it's going to be the determinant of u times this factor squared e to the I phi. So anything with determinant e to the I phi can be written as the product of a phase times something with determinant 1. Now, if I look at what that phase does to x tilde, if I just have a phase here, e to the I phi u dagger minus I phi times x times e to the I phi u, the phase just comes out because it commutes with everything. So the phase of this matrix doesn't actually transform x at all. And so I can choose the determinant to be 1 and I haven't lost any transformations. The phase is a trivial transformation that commutes with all the others. So I can choose the determinant of a to be 1 without losing any information. Right? That satisfies the necessary condition, but it's also sufficient to give me all of the transformations that preserve the determinant of x. And then I want trace 0. So the trace of x tilde needs to be 0. That's the trace of a dagger x a. And by the cyclic property of the trace, I can write that as the trace of a dagger x. And so I want this to be 1. I want a dagger to be the identity, and then that'll be the trace of x, which is 0. So I get the condition I want if I take unit determinant unitary matrices, and the group of such things is called special unitary 2, or SU2C if you like. But unitary suggests that we're talking about complex matrices here. Questions?
Yeah, I have a question. Could you remind me, you can take the determinant of the product of matrices and split them up into the determinant of the individual matrices multiplied together, correct?
That's right, yeah.
So you could have gotten the unitary condition that you got from the trace still with the determinant, couldn't you? If you had split up and then just rearranged the order and then recombined, you would have ended up.
That's what I split it up here. So this is the determinant of A dagger X A. That's the product of 3 determinants. I used something I didn't say explicitly, sorry. That the determinant of the transpose equals the determinant of the matrix. That tells me that the only difference between the determinant of A dagger and the determinant of A is one is the complex conjugate of the other. So, so this is the complex conjugate of that. That's what enabled me to write it this way. So yeah, I'm sorry, guys. I'm kind of racing through steps here because I just did a quantum class right before this. You remember? And I'm sort of changing gears. But yeah, just stop me if I say something that's not clear. Yes, this step came between these two. All right. So you split it up. Then I should have said the determinant of a transpose is equal to the determinant of the matrix itself. And the adjoint is the complex conjugate transpose. So this determinant is just the complex conjugate of that one. So the squared norm of det A has to be 1. That makes it a pure phase. And a pure phase doesn't do anything. So we might as well take the determinant to be 1. We could specify it to be anything we wanted, but the phase just never does anything to X. Okay, so what we've just shown, perhaps a little haphazardly, but we really have shown this, I think, if you put the parts in the right order, is that the special unitary group in 2 complex dimensions, where special means unit determinant, U means U dagger equals U, is a linear representation of the rotation group. So let me be more clear about that. Let's let U be an element of SU2. Then for all X, let's see, equal X dot sigma, U dagger X U X tilde is also of the same form, is also a linear combination of polymatrices, because this is Hermitian and traceless. But also this preserves the determinant, and so det X equals det X prime can only be true if X squared equals X prime squared. And therefore, the transformation from XX prime is a rotation. Isn't that weird? So here's a way to write a real 3-vector as a 2x2 matrix, Hermitian matrix, traceless matrix, but a 1-to-1 onto mapping between real 3 vectors and Hermitian traceless matrices in 2 dimensions. And a way to write transformations of that Hermitian matrix that preserve the Euclidean norm of that real 3 vector. So this is a rotation. Now, I'm starting to feel like I should really prove this. That
So I do have a question.
yeah.
What is the what is the form of this x vector, this lowercase x vector?
It's a real
3 by 3 matrix.
Yeah, a Euclidean 3 space. It's a real 3 vector.
So it's just 3 space coordinates.
Any yeah, x, y, and z. Any real 3 vector. These are real numbers. So take any x, y, z element of R3. Okay.
Yeah.
And this is a one-to-one mapping between elements of R3, vectors in R3, and traceless Hermitian 2x2s.
Yeah. I guess I was struggling with like, what's the operation between x and sigma? Because sigma is a two.
That's a dot product. This is ordinary dot product, except these happen to be matrices. So what this means is I take
I understand.
sigma 1 plus y sigma 2 plus z sigma 3.
That clears it up.
Okay, good. Yeah. Are there other questions? Yeah. Okay. Yeah. I thought, you know, maybe you guys had seen this stuff before and I didn't want to rehash old stuff, but
I've seen it for sure. I want to make sure I'm got this notation all sorted out.
Okay. So have you ever exponentiated a linear combination of the J's to get those? Yeah. Oh, okay. Let me back up here. Let me back up. Let's see.
And Professor, I had a quick question so I'm on the same page too. So is the geometry of the picture that in the SO3 picture, we've got like a three coordinates, and then we're rotating all 3. But then in the SU2 picture, we just have a plane, right? But then we're rotating like this. Is that the one is maybe quote unquote on the tangent, like one is like local, one is the flat picture, and the other is
it's worse than that. Okay, because these guys are these are transformations of C2, a 2-dimensional complex space. So really a 4-dimensional real space, right? You know, rotating a complex plane, you know, yeah, some of these will do that, but you know, they could actually be mixing up, you know, 2 complex numbers. So it's not quite that easy to picture, but yeah. So, all right, 3 dimensions. We've got like, yeah, X, Y, and Z here, X, Y, and Z. And so I picked some unit vector N and I'm gonna rotate around that. You know, that's what we're describing. And that's the easiest way to think about a rotation. But an equivalent way to do that same rotation is to take an element of SU2. Well, an element of SU2 is the exponential of an element of the infinitesimal generators of the unitary group. I can write it as e to the I phi n hat dot polymatrices, because the polymatrices are actually the generators of SU2. We'll show that in a minute, you know, but here's where a difference comes in. These things act on a vector space, right? They're linear operators on a vector space. That's C2, you know, 2 complex dimensions these act on. They also act, all right, this object is a tensor over that 2-dimensional vector space. All right, this is a rank 2 object. And in order to rotate this using these, I use 2 of them. It's a similarity transformation of a matrix now. This is why there's a 2-to-1 mapping between SU2 and SO3. And, you know, I think we should probably really work through this in detail. So, yeah, here we go. Let's do this. You guys okay with this? You know, yeah,
just quick
Yeah.
question of curiosity
Yeah.
about where we're
Yeah.
headed here.
Yeah.
This
Okay.
point that you've made about SU2, the 2-to-1 mapping here.
Mm-hmm. Yeah. I'm going to
Is
do
this
it.
where the, yeah, we're about to head, but is this where this, these weird paradoxes come from, like that belt trick?
Yeah. Uh-huh.
Okay.
Yeah. Yeah. If you look at the space of parameters here, to bring one of these back to itself, phi will run from 0 to 2 pi. But remember, these also act on a column spinner. A spinner is the two-dimensional complex thing this acts on. Going from 0 to 2 pi takes that spinner to minus itself. So because this is transforming as a rank 2 thing, 2 pi brings it back, but it doesn't, that's not the same SU2 transformation as the identity. You have to go through 4 pi to bring this back to the original transformation. So Lie group is also a manifold. The manifold of transformations for SU3 goes out to a radius of 2 pi. The manifold for transformations of SU2 goes out twice as far. And whereas, I'll do these manifolds for you after. You know, this, we should, okay, for next time, read, what is it, chapters 3 and 4, 4 and 5, I think, in the gauge theory book. You know, I go through a lot of this in detail. I'm going to start the calculation now. And, you know, if we don't finish it, you know, we'll finish those chapters. Let me see. Well, I won't pull that up right now, but read those chapters of the gauge theory book. You know, I think it'll clear up a lot of this because I went through it in detail there. But let's just do this whole thing explicitly. So you can see it. So first off, I'll show you how to do real 3-dimensional elements of SO3 and convince you that we really get rotations. So the Euclidean 3 metric, I'm going to write as delta ij. It's a 0-2 tensor, right? It's not the Kronecker delta. It's a 0-2 tensor. But you know, we don't care. It still looks like the identity, and we're just going to use Cartesian coordinates, so it's fine. But I want transformations O, I, K, O, J, M that leave that alone. That's what I mean by, this is just like the Lorentz group preserving eta, right? You know, so x prime squared equal x prime squared, if and only if the transformations that I act on x with, x I prime. So I'm going to apply a rotation matrix to x and insist on it preserving length. And if I turn that into a condition on the metric, I get this. Everybody with me on that? Okay, I see a thumb up. I'll take that as being 5 thumbs up. 2 thumbs up, okay. Is there a question? Thumb halfway up? Okay, I'm going with this. You know, if you, yeah, just write this equation, substitute this in, and shuffle things. You get this condition as equivalent. Now, now I let O be infinitesimal, and I write out this condition. Well, actually, this condition, notice that normal matrix multiplication is like that one times that one. This is actually O transpose Ki delta I J O J M. This is O transpose delta O equals delta. If I write it in proper matrix multiplication, you're always summing adjacent indices when you multiply matrices and components. So the transpose here is delta ki plus epsilon ki times delta ij times delta jm plus epsilon jm has to equal delta, where are km? So we just write out the condition. Now we multiply things and look to first order. These two on that.
Did you, sorry, did you take the transpose? Am I missing something?
Yeah, ki.
Okay, yeah, I see.
Okay, so yeah, that's second here. I hope that works right that way, but yeah. Yeah, if I'd done it in this notation, I'd just write epsilon transpose and it would be clearer, but this works. So the three deltas, that's going to lower this to a delta im. So I'm going to have delta ki, delta im is going to become delta km for that first one. Then here, this lowers this to an epsilon kj, and this changes the k to an m, so I get epsilon km. Wait a minute. That's not right, though, is it? I didn't get the transpose here. Oh, rats. Km. I want mk. I'm not getting mk out. Why not? Let's see. I want epsilon transpose the ki component. All right, this is epsilon transpose, the km component. Then this one, this becomes im, that makes it km plus epsilon, plain epsilon km, plus order epsilon squared that we drop is delta km. Okay, so those go out, and now we get the km component of epsilon transpose has to be minus the km component of epsilon km. That means epsilon has to be anti-symmetric. Okay, that's right. Yeah, I needed transpose here. So I took a transpose up here. So OIK I can write as O transpose KI. So I needed the transpose here. Sorry. Okay, so epsilon has to be anti-symmetric. And that tells me that epsilon has to be some linear combination of those three j's. All right, so I wrote the j's before. And there's a clever trick to how I assigned the j's. What I do is for the ith j, I use the Levi-Civita tensor. So J1 is going to be, all right, this is 1. This has to be 2, 3. So row 2, column 3 has to be +1. Row 3, column 2 has to be -1, and everything else has to be 0. So this is just a way to assign the right numbers to some bunch of anti-symmetric matrices. So you can write out J2 and J3, and you'll see they're the ones that I wrote before. So this is handy because this having this particular assignment for basis makes it easier to take powers of the thing, which is what we have to do to get the full rotations. So now, is everybody good to this point? Let me, everybody pause, take a deep breath. You have any questions up to this point?
I just see the bottom of the board again real quick.
Oh, sorry.
Oh, that's all you, that's what you wrote. Okay. I just needed to see what was there.
Okay. Good. Okay. So now here's this little calculation. So it's worth remembering that an infinitesimal rotation is accomplished with an antisymmetric matrix. That's useful in itself. Like when you do all this with differential forms and want to write the spin connection, it's antisymmetric, it's an infinitesimal rotation. you're preserving an orthonormal basis. We're not there yet, never mind. Okay, so let me take G of W to be the limit, and I'll just do this for you, of the identity plus, let's take an infinitesimal linear combination of these guys to the nth power, where n epsilon has to approach my vector W. Okay, so by doing an infinite number of infinitesimal rotations and the limit of the infinitesimal going to 0, I can accomplish quite rigorously a finite rotation. So we do that, and I can do that by writing the binomial theorem. Something to the nth power is the sum k equals 0 to n choose k, epsilon dot j. It's symmetric in k and n minus k, so I can take this to the k and I can take 1 to the n minus k, and then I don't have to worry about n minus k. All right, so I can expand a plus b to the n as this expansion, right? And now a is epsilon dot j, and b is just 1. And now let's write epsilon vector as some small epsilon times a unit vector n. And then I want the limit of the sum, n factorial, k factorial, n minus k factorial. Then we have epsilon to the k, n dot j to the k, and 1 to the any power is 1. Everyone with me? So now what I want to do, I need a bunch more n's here. So I'm going to multiply by n to the k and divide by n to the k, because I can, and then I can combine those two into the magnitude of W. Let's write W a similar way. Let's write W as some magnitude times n hat. All right, so so if I take n of these things, n times epsilon is approaching that theta. So n epsilon goes to theta, and the n comes along for the ride. So, right, I'm using n in two ways. N is an integer here, n is a unit vector there. The hat on it tells you it's a unit vector. Okay, so let's write this out. Now we have, right, n factorial over n minus k is n minus 1 down to n minus k plus 1. Then I have a k factorial that's still there. And then I have n to the k from here. And then I have w to the k over here. I have n dot j to the k there. And these factors, we're summing k equals 0 to n. All right, put one of these denominator n's with each numerator thing. So I have a 1 over k factorial, and then I have n over n is 1. Then n minus 1 over 1 is 1 minus 1 over n. And so on down to 1 minus k minus 1 over n. And w to the k, n dot j to the k. And you can see, okay. Now, there's a finite sum. The limit here is a product of a finite number of things, each of which is approaching 1. So that's going to go to 1 in the limit. And what I'm left with is 1 over k factorial the limit goes to infinity, and I have a power of W, I have a power of this matrix. So the final result, taking the limit, is the Taylor series for the exponential, which is well defined. That's the definition of the exponential of a matrix, is the Taylor series. We know how to take powers of matrices. So it's totally well defined to write the exponential of W n hat dot j. So the exponential of an arbitrary element of the Lie algebra is what we end up with here. So that's the thing I glossed over before. Questions on this one? This is just, rearranging the combinatoric factor, really. But
it's a kind of a simplistic question, maybe. What does the exponential of a matrix look like exactly?
I'm sorry, I just said it's defined as the Taylor series of the matrix. So take the Taylor series for an exponential, and now you're only putting in powers of matrices. All right, those are well defined.
Gotcha.
It's a transformation. It's a 1-1 tensor, these J's. So I'm actually going to carry it out. So what we need in order to know what this is are powers of n hat dot j, where n's a unit vector. So I'm actually going to evaluate these group elements. So these group elements end up being e to the theta n hat dot j, where that means this sum, 1 over k factorial powers of the exponent. That's what it means. So now I'm going to go backwards and actually work this out. To do that, I need n dot j, all right, say squared. So what is that? Well, remember I chose the components of ji to be epsilon ijk. And I know how to work with the Levi-Civita matrix. So I can actually do this. This is ni epsilon I jk. Properly, jk, it's a matrix, but our metric is the identity here. Times n m epsilon, let's see, m, here, you want to, let me put indices in the proper positions just because. Okay, so now we need k n, like that. All right, so ni, nm. Yeah, let me just drop all the indices. It's just easier to see. I want to shuffle that k to the n, so I'm going to get a minus sign. So I need to work out epsilon I j k epsilon m n k. I've interchanged those two. It gives me a minus sign. And now, if I sum two Levi-Civitas, I have to have either I equals m and k equals n, or I equals n and k equals m. We worked through this identity in a little more detail last time. I n delta j n, and trace here is 3 times 3 is 9 minus 3, that's 6, and that's 3 factorial, so there is no coefficient here. This is exactly it. So ni and m, and I get a fairly simple matrix. Let's see, I m, that gives me n squared delta j n. Then the second term gives me n sub n, wait a minute, that was an m here, n sub j, like that. So the matrix I get is built out of the vector n. And it's convenient to give this its own name, because this is going to come up again and again. But that's what this matrix, this is going to be the Jn component of n dot j squared. Okay, this feels a little complicated, right? But it gets simpler because if I cube it, cubed, and I'm going to want like the jk component. That's going to be this times one more. So what's n squared? It's a unit vector. So this is just one. So I have minus delta jn plus n sub n, n sub j. And then I'm going to multiply that times n, let's say m epsilon m, and now I'm contracting n and getting k. So that's the product I need. And okay, delta jn on that gives me n sub m epsilon m j k. And then n on this, all right, I've got n and j and m. Contracting on an mn, all right, I've got, this is an n sub n and n sub m on epsilon m and k. That's the cross product of n with itself, the kth component of the cross product. That's 0. So I get this, let's see, probably with that minus sign, I believe, m, j, k, yeah. This is minus n dot j.
Can we angle
J,
that
K
camera?
Sorry?
Check the camera angle. Thanks.
All right, yeah, thank you. Okay, so when I cube it, it comes back to minus itself. And that's going to let me sum the whole series. If I take the fourth power, then it's just going to be the minus sign. Let's see, it's cube times, it's this thing squared. Let's see, how do I take the fourth power? I'm taking this times one more, which is just minus this times itself. So it's minus this matrix again. All right. So I'm going to get alternating signs, but I'm just going to bounce back and forth between n dot j and this funny thing. So I can write out the whole series. Let's give this guy a name. Let me call this, what's the name? I'll just call it MJN. All right, so that's some symmetric matrix. So I have MJN is minus delta JN plus NJ and M. And now I can write powers of these things. So n dot j to the to odd powers 2k plus 1 is going to be minus 1 to the k times n dot j. I did the sign business quickly there, but that's right, because when k is 1, I'm talking cubed. That's when we got the first minus sign. When k is 0, that's just the thing. So this works. And then m to the, or sorry, n dot j to the 2k is going to be, well, it's this matrix M, but that's going to alternate signs as well. So when we go to the next one beyond this, that minus sign survives. So I multiply in one more, I'm getting the thing squared times a minus. So when, let's see, n dot, wait. When k is 1, here, let's do it this way. Let's put a minus sign in that. So this is minus m. So when k is 1, I get minus this m, and then alternating powers up from that. So now I've got all powers of n dot j, and I can write the exponential. All right. Everybody good with this? Okay. So evidently what I need to do to write a general rotation is to sum the even and odd terms. So let's let k equal 0 to infinity. 1 over, all right, 2k factorial times, right, even powers. So I have minus 1 to the k, m times m, times theta to the k. Right, remember, we just found powers of n dot k. We just found powers of n dot k. There's still that theta to the k, that amplitude that keeps going up. So this is the even powers. I just have to worry about the 0th power. Let's see. When this is 0, well, everything is 1 here, but I don't have an m, so we better go from 1 here. Right? So when we'll have to worry about when k is 0. When k is 0, there's just a 1. Right? So the 0th, so expanding the exponential, the first term in the series is just the identity. And then we have another sum, and now we can take k equals 0 to infinity, 1 over 2k plus 1 factorial, minus 1 to the k. And now we have n dot j, and we have theta to the 2k plus 1, and that really does start with k equals, let's see, k equals 0. So n dot j to the 1 is n dot j. We get theta to the 1. Yeah, okay, that's good. Everybody happy? So that's the Taylor series for the exponential. But now you see what we've accomplished is each term here has m, and I can bring it out of the sum. Each term here has n dot j, I can bring that out of the sum. And I can do those sums. And we almost know what those sums are.
So I'm sorry, I don't quite understand what the second sum is.
This one?
Yeah, what is this coming from?
We're summing over all odd powers.
Oh, these are the, oh, of course.
So
of course,
yeah,
now it makes sense.
So,
Yes.
so this is 1 over k factorial theta n dot j all to the k.
Yeah, it just took me a second to see
But I've
that.
separated the even and
Yeah.
odd terms in the sum.
Yeah,
I've separated out the 0th term, the even terms, and the odd terms.
got it.
Okay, so what I have to do here is I need to add and subtract something. So if I write the matrix M times the sum k equals 0 to infinity minus 1 to the k theta to the k over 2k factorial, you know right away what that is, but I've added a term, so I have to subtract m times the k equals 0 term, which is 1 here, and 1 there. So I have to subtract an m. And then this term is n dot j. And then I have another sum that you recognize. So if you don't recognize now, you will after this. What are those sums? The even and odd terms of the exponential.
Sine and cosine.
Sine and cosine, good. All right, so I get 1 minus m plus m cos theta plus n hat j sine theta. And all right, so now we don't have enough time for me to do this, but the easiest thing to do to sort this out, and maybe this is a good problem for you guys to think about for next time, if you let this act on a vector x, then choose an orthonormal basis where n hat is one vector, then n cross x gives you a vector perpendicular to that. You normalize that, take the cross product of those two and get a third orthonormal vector. If you write out the action of this on an arbitrary 3-vector x and put it in that basis, here's what you'll see. We can do it next time if you guys don't all manage it as homework. But what you see is the parallel part to n is just the identity. So the part of x, n dot x, doesn't change. It just comes right through. Then the two orthogonal parts, one transforms with a cosine, one with a sine. You know, it's just the rotation of the plane orthogonal to n. And you can see that explicitly if you just let this act on a general 3-vector and decompose it in that basis. So you want to decompose it along the n direction, the part of x perpendicular to n, and the part of everything perpendicular to that. You'll see that you get a sine cosine 2-dimensional rotation of that plane. So you can directly interpret this geometrically. Okay, so homework for Monday, do that for SU2. SU2 is going to give you this same formula. So remember the x and the x prime. If you do this, so if you have this capital X is some x dot sigma, and x tilde is e to the I phi over 2 n dot sigma with a minus and times x times e to the I phi over 2 n dot sigma. You expand all this out using identities on those guys. So maybe you do or don't know those. I'm not sure. But you know, this is going to be. We have proved that this will be Hermitian traceless, and so we can write it as some linear combination of the Pauli matrices after we go through all of this. That x will be related to that x via this formula acting on x. What happens is this is quadratic in phi over 2. You get a bunch of double angle formulas that turn that into phi. So you get a rotation by phi about n. We'll get the same formula. We can work through all of that. Try it on your own. Read those chapters in the gauge theory book on Lie groups, because I go through all this. And then, you know, come either with questions or answers, and we'll work through as much of it as you want to see next time.
Are there assigned problems like you're doing for quantum, or how is this working?
I've just assigned you. I should write these up. Yeah, let me write you some problems. I think the books have some exercises. You know, yeah. Alex was just asking, should we work the exercises? Well, hell yeah. You know, you're trying to learn quantum field theory, right? So you know, work out everything. But yeah, let me try and come up with some problems for you too, some specific ones. But yeah, the goal is I want you to understand this stuff, right? So work it out, and if you have questions, ask them. We'll work through it. Okay, all right. So yeah, I'll see if I can't post some suggested things to work out. Okay, I can stay on if you still have questions, but I know a couple of you have to go. All right, see you. Oh look, Alex is still here.
Nice.
Yeah.
Yeah, okay, I guess I do have just trying to visualize that. This is what caught me up in just at the end with Dr. Tori's class a little bit. It's just
Okay.
visualizing the in general between this difference we've done where we've gone from an orthogonal group to a special unitary group. Like, I guess just trying to visualize this, I got kind of caught up in, and because this is the SU2 representation is the adjunct, the adjugate
Adjoint.
I'm saying stupid things. Yeah, the adjoint representation of the action, right? And then the SO3 would just be the regular space interpretation. Am I thinking of this right?
Yeah. Well, let's see. No, one's not the adjoint representation of the other, but okay. SO3 is, all right, let's see. Let me back up and talk about representations of rotations. This is in the notes, okay? Coming up somewhere in chapter 3, I think I run through this. I actually sometimes do it in quantum mechanics class, but all representations of the rotation group. And the way you get there is from the Lie algebra satisfied by the J's or the Pauli matrices. You know, two generators commute to give epsilon ijk times the third generator. Right, so you know there's a two-dimensional representation of that Lie algebra because the Pauli matrices do it. So you know you can't diagonalize more than two matrices at once. You can take them to be the sum of the J's squared and JZ. You can take those two to be diagonal. So then all vectors that that your representation act on can be labeled by the eigenvalues of J squared and JZ, which is what we do. You know, we call them J and M, right? And now by acting
it's like a block. You're like turning the matrix into blocks and then identifying those blocks as just
yeah,
right?
yeah,
Okay,
so,
sorry.
Yeah, so what you show is you out of JX and JY you can make raising and lowering operators. You've probably seen that. JX plus or minus IJY will leave J the same but change M.
Okay, that's familiar.
You know, you work it out, and it does. It's in the notes. It's in the notes coming up, so you'll see this. All representations of the rotation group. Now, so what you can do is you can keep raising M or keep lowering M until you get something idiotic that has to be 0, and that shows you the full range of M for any given J. Then let me think. What do? It leads you to some inequalities that lets you put limits on J and M. And what you find in the end is that J can take any half integer value. And M will run from minus J to plus J in integer units. That means that for any given J, there are 2J plus 1 possible states, possible components to your vector. All right, but J takes half integer values, so 2J plus 1 takes every integer value. So there is a representation of, a vector representation of the rotation group in every dimension, every 2J plus 1.
Okay.
Right, and these, all right, these are things with total angular momentum of J plus 1 actually, but we just call it J, of 0, 1/2, 1, 1.5, 2. And these tell us what kinds of fields exist in field theory. We can have scalar fields, spinor fields of spin half, vector fields of spin 1, Rorita-Schwinger fields of spin 3/2, the metric of spin 2. Those are all we've seen. Those are the only spins we've seen. But this analysis of all representations of the rotation group tells us what kinds of different field we can expect to have.
Okay. Yeah. Okay.
All right.
And then so is one of these representations, yeah, okay. Sorry. So is one of these representations like is SO2 looking like, sorry, where we label the quantum numbers from -m to +m, and then the other one is looking like where we're labeling things by 0, 1/2, and 1. Is that the difference between these representations that's happening? Or like one is represented by 2 quantum numbers, -m, total j, the other one is.
Yeah, okay. So
Sorry.
this is, this gets into irreducible tensors, which is like it's sort of boggling. But let me give you an example of what's happening here. We're used to dealing with various sorts of vector space. You know that you can take linear combinations of matrices; they form a vector space. So, for example, we can look at say 3x3 matrices, right? And those form a vector space. They form a 9-dimensional vector space. But any matrix like this can be written as a symmetric part, traceless symmetric part. So what do we need? Delta I, J, M, the trace. Now, if I trace that, I get 2 traces, and I'm going to get so I need like a 2/3 here to make it traceless, I think, plus an anti-symmetric part, plus a trace part. Probably, let's see, I need to add in 1/3 times MKK. So it's easy to see those add up to the original matrix. But now, under rotations, each of these maps into itself. These are invariant subspaces of that 9-dimensional vector space. So these are the irreducible representations of that 9-dimensional vector space. And notice what the dimensions are. This gets even stranger because traceless symmetric 3x3 has 5 degrees of freedom. So this is a j=1 vector space. There are 3 of these. So that's 2j plus 1. Sorry, this is j = 2. This is j = 1. And there's 1 of these, that's j = 0. So this is a scalar, this is a vector, this is a rank 2 tensor. Under the action. So a j = 1, a j = 2, and a j = 0 decomposition of this 9. So this is, you would write this as a 3x3 thing, but we can decompose it into a 1 plus a 3 plus a 5 as irreducible subspaces.
Yeah. So this is what do they call those the something Gordon, the Clebsch-Gordon
coefficients, yeah, and the Wigner-Eckhart theorem, and yeah, this is the Clebsch-Gordon decomposition. You'll find, let's see, pretty soon you'll realize you're dealing with spherical harmonics too. Yeah, those are irreducible representations of something or other. I forget what, but yeah, there's a whole lot of group theory that sort of folds in here, which may or may not be necessary to completely master, depending on what you're doing. But this is a nice example to remember if you're trying to think about irreducible representations. So these JMs, when we characterize a vector space that the rotation group acts on by the total spin and the z component of spin, basically, these are irreducible representations of the rotation group. And there's one of those of every dimension, each integer dimension starting from 0 on up.
that then each of those spaces has different dimensions. Or
Yeah,
sorry,
yeah.
we're saying the same thing.
So for each j,
there's
each j gives a space of dimension 2j plus 1, right? Because m runs from minus j to plus j.
with 0.
Right. So changing m gives you different components of a representation of dimension 2j plus 1.
So like so then the conserved quantities, like the Noether current and all that we're gauging out, that's like, so we've set up this spin matrix, these poly matrices to, like, I guess it's controlling the gauge, but it's relating all the conservation directions to each other. And then we have a law there, and then we're conserving that, right? So we've spin up and spin down that we're conserving at the same time, as opposed to conserving each independently. So instead of like having like a negative charge that instead of in electric charge where we conserve positive and negative charge or total charge, we're like conserving spin interaction almost. I'm just trying to, I'm trying to interpret the adjoint representation.
You're jumping ahead with too many ideas at once. Okay, the adjoint representation for a group is, let's look a little bit at Lie groups. You know, it's a different thing. It's, you know, we're not dealing with that here specifically. But let's look at what it is. If we have, suppose we have a Lie algebra, right? Then we have some structure constants, anti-symmetric here, and we come, it closes back into the generators. And this gives an anti-symmetric product on every linear combination of these guys too. Okay, so I can have, you know, well, this could be any representation I like, but there is a particular representation, and you know, mathematicians don't define it this way, but I do, because I just want to work with these things, right? If you take matrix components of G to be, let's say Kj. This could be off by a sign or something, but take these to beCijk. It works because of the Jacobi identity. If in the Jacobi identity you substitute these guys for the commutators, then the Jacobi identity turns back into this. All right, it shows that the structure constants actually give a representation for the G's, for the generators. And that is, you know, the physicist's definition of the adjoint representation. Maybe not a mathematical physicist's definition, but you know, you'll hear other ways in the math department that are equivalent to that. That, you know, when you put it into actual matrices, it turns into this.
So then we're like when you do it in this representation, you're doing something like conserve, like when you do the charges and whatever that you're conserving, you're like conserving the structure constants. Is that something that, like, well, and they represent a law, I think, like, right, they're representing a law, but you're propagating that law appropriately. Like, it's something's being conserved, but you're like measuring off of the structure constants to get it.
The structure constants contain invariant information about the group. Now, I can take linear combinations of these and get different structure constants. So when you do something like Dinkin diagrams and try and classify groups, what you do is you choose these sort of one at a time to make these simple. You know, there's a kind of canonical way to construct these so that you can prove theorems and prove that you've found all the algebras of a certain type. There are things like that that people do, but the invariant properties of these guys, if I use this representation, I can prove a lot of theorems. So, so for example, if I take the trace of a pair of generators, define that to be some Kij. Right. Well, that's a group invariant thing, because if I change the basis here, all right, I can define a new basis by pretty much any linear transformation. So I take lambda inverse G lambda, then this product is going to be the same, because right, G tilde is going to be lambda inverse G lambda, lambda inverse G I J lambda. This just gives me 1. So I get lambda inverse GI GJ lambda. But now if I take the trace of that, the cyclic property of the trace kills the last 2 lambdas. Oh, I'm sorry, you can't see what I'm doing. The trace of this, those lambdas go away. And so I see that trace of G tilde is the same thing. So this is independent of the representation of the group. This is called the killing form.
Oh.
And it's
sure.
metric. I can write it in terms of the structure constants, and it turns out to be C I J. Okay, let's see. What do I got? I J. C I C. C K J M. Doubly summed, so a trace of a product of the structure constants. If I use the adjoint representation, the killing metric can be written in terms of the structure constants. And now, if I've worked out my Lie algebra for, say, the conformal group, I can pull the structure constants right off, and I can compute this thing, and I can find, oh, it's this matrix, and that's independent of the representation of the group.
Man, wait. So wait, is this saying like the killing form is something like the outer product of the structure constants, or what? This is like a breaking of them. But
it's a trace of an inner product. It's multiply them. Yeah.
Yeah. Sorry, it's a partial inner product.
Multiply them and take the trace.
Mm-hmm. So okay. So it's the trace of an outer product. Is that one way to say it? It's the trace of the outer.
Well, now it's an inner product, right? We sum K here, right? So right here, G I is a transformation matrix, call it JK, and then G. Well, let's see. Let's say MK G J components K L. All right, I multiply them, and then when I take the trace, I'm setting L equal to M. But then I said this is a structure constant C I. Did I reverse it? Yeah, K M. This is C J M K. So I have a double sum here on the structure constants.
Okay. Mm-hmm. It's that double sum I'm trying to interpret.
Oh, so
just yeah, more.
The sum on K here is just the product of 2 generators. The sum on M is the trace of that product.
Okay, I see. Yeah. Okay. Yep. Trace of an inner product. Okay.
Yeah. It's literally just this in the adjoint representation. Yeah. So it's sort of the difference between finding abstract properties of group and actually being able to, compute them for a particular group.
Let me write this. Let me write this down. My mind's exploded. Okay.
Oh, okay. Can't have that.
No. So this is okay, and this is one way to see that the structure constant is like curvature. Then, right? That it's directly related to a killing form.
Okay, the killing form is necessarily symmetric for a I believe a semi-simple group, it's non-degenerate. Right, so, you know, if you've got a group that's, you know, like a billion, this thing's zero, right? The structure constants are zero. So if you have a simple group, this will be non-degenerate.
Okay.
So SON is non-degenerate.
Okay.
Now, let's see. I use this guy. This actually turns out to be really useful in doing some geometry. So, you know, I write the Lie algebra as Maurer-Cartan equations. I don't know if you've seen those before in differential forms. Okay, this so far what we're writing here, these are a basis for a vector space. This is a vector representation, but I can define some one forms that contain the same information.
Okay.
And those are called the Maurer-Cartan equations. And Cartan developed a technique for constructing curved geometries from the Maurer-Cartan equations. The Maurer-Cartan equations describe a group, describe the group. They are a connection on the Lie group. But the Lie group is a very simple manifold. It's, you know, it's homogeneous, right? It's, I mean, it basically looks the same at every point. You know, I can transport the identity to any point in the group, and that neighborhood will look just like a neighborhood of the identity. That's why we can use the Lie algebra to get the whole group. Well, the Maurer-Cartan equations, you can twiddle them, right? So you've got a connection on the group manifold. You can change that connection. And now you've got a curved space, right? And so you've generalized, now you've got something that looks locally like the group structure, but it's different. Now you're describing a curved manifold. Now, some of the Maurer-Cartan forms, some of the one forms dual to these generators. So suppose we're describing the Lorentz group here. So we've got some Lorentz transformations and we've got some translations. So a Poincaré group. Let's do Poincaré. Okay, so I write the Maurer-Cartan equation for the Poincaré group. Well, the one forms dual to translations. Let's see. How do I do? There's another step here where I take a group quotient, but you know, by taking a quotient of the Poincaré group by the Lorentz group, I build a fiber bundle where the fibers are Lorentz and the one forms dual to the translations span the base manifold. They become an orthonormal basis there. How do I define orthonormality? Well, yeah. I can define an inner product equal to the killing form, but I can't do it in general relativity. I can do it for the conformal group though. You know, it depends on what quotient I've taken. But okay. Sometimes I can use this invariant form to define an inner product of my basis one forms. And I'm able to do that in biconformal space. You know, it doesn't work for Poincaré because Poincaré has this abelian part and K is degenerate.
Okay. Okay. So yeah, when you're setting this form up, so in that dual space, we're doing this locally in the fiber bundle. This whole process, then, right? Is that am I saying this right? And then it's only non-trivial when that fiber bundle or when the bundle is dependent in space, because otherwise it's just a trivial co-space to your base and your manifold. Is that?
You lost me. Sorry.
No. That's the basic idea I'm saying is that you're doing this transform locally on the fiber bundle space, and if the fiber bundle space is identical everywhere, then it's a trivial connection between fibers, right? If you have a Poincaré symmetry, then the tangent space should be the same at every point, and so the connection is trivial, and so that's why the killing form is zero. But in order to define
the killing form is zero because if you go to the Lie algebra of the Poincare group, right? The Lorentz group is SO3-1. It has a non-degenerate killing metric. So if I have rotation matrices, right? This goes like, C with C and M stuff, right? Lorentz transformation is closed. This is subgroup. And then I can act with one of these guys on a translation. And it turns out that's, well, it's an infinitesimal translation. It's something like delta I, K, Pj minus, it's plus or minus this anyway, minus delta I, J, dk. Is that right? Let me put this down.
Sure. Yeah.
So I can see what I'm doing. So I'm going to get a delta IKPJ minus delta JKPI. Right? That's something like that. And then, but then translations commute.
In Poincare, under Poincare. Well, yeah, because we're flat. Yeah.
Yeah. Right. Yeah, we're just doing, Poincare on space-time. So those guys commute. So the structure constants here are 0. So if I look at the structure constants, whatever here, and construct a killing metric, these give a non-degenerate killing metric. The Lorentz group is an orthogonal group, pseudo-orthogonal, has a non-degenerate killing metric. It's a simple group. But this is not having all these things that commute. So when I construct the killing metric for the Poincare group, it's, I get something, J, K, I get something like this in the Lorentz sector.
Yes.
I think I get zeros here, but I get 0 here too. For this is
for the killing. Yeah.
This is from this guy.
Yes.
And so now, when I do this construction that I was all too briefly describing, can you hear me okay when I face the board and talk?
It's all right. I'll let you know if it.
Okay.
Yeah. Okay.
So,
Thank you.
so these give rise to Maurer-Cartan equations. So corresponding to each generator, I get a 1 form, and I give them these names. So these are dual to the P's, and these are dual to the M's. In the usual.
What was the other dual? I'm sorry. Oh, I got you. Okay. Yep. E. Yep.
Okay. So the Maurer-Cartan equations contain all the information of the Lie algebra. I, J, K, omega, I, K, D, E, I is E, J, omega, I, J, right? These are the same as the commutation relations. That's this. The integrability condition for these, well, d squared equals 0. The integrability conditions for these are the Jacobi identities, right? Now, if I take a quotient of Poincare over Lorentz, that gives me a fiber bundle with a 4-dimensional manifold and Lorentz fibers. All right, so taking a group quotient is basically identifying with 1 point everything connected by a Lorentz transformation. So a group quotient of a Lie group by a Lie subgroup is always a manifold, and a fairly trivial one. So in fact, here it's space-time. So we get space-time back. Now, I could try to say, oh, I want an inner product on my basis 1 forms.
And you're gonna.
Well, I'd like to be able to say that I take the invariant killing form for that. but that's zero. So that doesn't work here. If I do the same thing in a quotient of conformal by the veil group, it's non-degenerate there, and I can define the inner product using the killing form. And that turns out to be the right thing to do, in fact. But it doesn't work for general relativity because that's zero. Now, the generalization to curve spaces, okay, this is a connection on the Poincare group. I take this quotient, so I have a base manifold and local Lorentz fibers. What I do is I say, oh, I'm going to change the connection. Okay, different connection, but these are no longer satisfied. So now there's some other stuff here. And what I know about this stuff is that it's a vector value 2 form, and this is a matrix value 2 form. That's the Riemann curvature 2 form, and I've just described every Riemannian geometry. And in fact, in any dimension. So I need some conditions on this for this to be right. I need T and R horizontal, which means that, for example, this 2 form can be expanded just in the form spanning the base space, not the Lorentz part. Otherwise, integrating this around a closed loop would depend on the lifting. I still want my Lorentz transformation. So making these guys horizontal means that I don't muck up my Lorentz fibers.
Mm-hmm.
The other thing is integrability. That follows from imposing d squared identically 0 on these equations. And it gives some differential equations on these. In fact, here it gives precisely the Bianchi identities. This is, T is the torsion. We usually take it 0.
Okay.
So if it's 0, this is the vanishing triply antisymmetric part of the curvature tensor. And this is the vanishing triply antisymmetric part of the covariant derivative of the curvature tensor. Okay. So those are the Bianchi identities in differential forms. So the Bianchi identities are the integrability conditions that I impose on the connection generalized Maurer-Cartan equations. So the Cartan equations, we need them to be integrable. So we need these differential conditions. So this is how I like to construct geometries.
Yeah.
And yeah, basically all you're lacking now is an action and you're doing general relativity. But you build it by taking the quotient of the Poincare group by the Lorentz group, generalizing the connection, imposing conditions on the connection so those equations are integrable and preserve the Lorentz fiber structure. Now you're at an action from the obvious available fields. So we're going to take torsion 0. So E is a tensor because, let's see, E is a tensor because when we generalize the base manifold, we lose translational symmetry.
Yeah.
So there's no inhomogeneous transformation for the solder form, and that becomes a tensor. So I can build an action out of basically the curvature and the solder form. And I can still impose the usual Minkowski metric as the inner product of the basis forms. Mostly because this connection respects that. I have Lorentz transformations, and that's a Lorentz invariant object. So I can do it that way, get the usual metric.
So in this, I'm sorry, this is maybe a silly question. Are both the torsion and the curvature then in the mod space? Is that where they're, well, I mean, do they have one-to-one representations in the mod space?
The mods, what?
This is stupid, maybe. I guess it would be the total space mod the fiber bundles or mod
Yeah.
mod rents, yeah.
Yeah, so yeah, they are two forms on the base manifold. So yeah, take so you've got a Lorentz fiber bundle over a curved manifold.
Mm-hmm.
So anything you do with these objects is independent of lifting. But choose your favorite cross section. Now there are tensors on that cross section.
Dang it. Okay. Wow. This is great. And is this I guess holds for any omega here is representing, it was just the fiber group action, right? Omega. So omega here we took to be Lorentz, but we didn't necessarily have to, right?
Oh, that's right. Yeah. So it's whatever I take the quotient by determines what's on the fibers.
So like in like I guess in Yang-Mills theory, So okay, yeah. So in Yang-Mills theory, the field lives in this E space and the base space, right? With the E vectors, and then the gauge is living in D omega. Is this right? These are where the one-to-ones are.
The gauge, the one-to-ones. Okay. Yeah.
I just don't know if they're identical. There might be
these guys still have gauge transformations. That's right.
Okay, that's where the gauge is. That's where we're doing the gauge transform is in the omega space. Is this right?
Yeah.
And then okay,
that's right. So,
and then the gauged fields lives on the E basis, the E tilde basis.
Here, suppose I do this and take the quotient by Lorentz cross SU2, SU3. Let's do SU3. Doesn't matter. Cool. All right. So what I've just done is I put SU3 on the fiber along with Lorentz, right? If I make it part of the denominator of my quotient, I keep that symmetry as a part of the fiber bundle.
Yes. And that's why you, sorry.
Yeah. So a nice property here is that if I do it this way, I'm actually constructing the manifold, the space-time manifold itself at the same time as building an SU3 fiber bundle.
Yes. Oh, is this the quotient space why gauge theory is magic right here, that we're just like adding product spaces and then quotienting out by the same product space? So we're like building a really complex space, but we know what the components are, and so we're modding out at the end.
Yeah, we have a lot of control here. That's right.
Yeah.
Let's see, is this how gauge theory is magic? No, gauge theory is magic because this is actually what nature does.
Okay, fair.
This is all cool math, but nature actually does this.
Okay.
So, yeah, nature likes this local SU3.
Okay.
Okay.
But just in a general gauging, when we kind of add freedom and create a more complex system, and then know that freedom reduces in a certain way, and that's being represented in a modulo later on in like the algebraic structure. I took an algebraic geometry class forever ago. I'm waiting. I think it's the new whatever that German word is, the Hilbert's theorem. I'm waiting till I can remember that again. But
okay. So yeah. So basically, these are your gauge transformations down here.
Okay.
You can do these transformations on everything, and this construction tells you what objects they're going to act on. So you can have whatever tensors come out of this construction. Mm-hmm. The field strength of the SU3, for example, will come out of generalizing the connection, because you're going to generalize the SU3 connection too, right? So we've got this guy is whatever it was, and we got this guy is whatever it was, but we also have generators of the what do I want to call them?
Right.
So A to I is structure constants for SU3 here.
Uh-huh.
J, A to K. that's an SU3 sitting right inside my set of differential equations. And so when I generalize, I add these curvatures. I'm also going to add the field strength. The SU3 field strength gets added here.
Okay.
Right. And this tells me what sign that I should use for my field strength, so that it actually is a tensor.
And then if you were going to couple this to U2, then you would throw on in another term, right?
Yeah. So standard model, boom, we got it. Sure, no problem.
Oh, I think this will help a lot. I'll go back to Tori's text. I'm in your gauge text right now.
Okay. Good.
This will help a lot. That makes a lot of sense. Holy crap.
Okay, so these methods, you're going to want to read the gauge theory book. I described this method in chapter 11. So work your way up to it. Make sure you've got all the prerequisites. Then I do a bunch of very simple gauge theory examples, simpler than any you've ever seen before, in chapter 10. And then I outline the general method, describe the general method in 11, and everything after that's going to be applying it to stuff. I apply it to E&M and general relativity in the subsequent chapters. But, you know, I'm planning on doing a bunch of other geometries as well eventually. Haven't gotten there yet. But chapter 11 is this method.
Okay, great. Yeah, when I was doing that before, I had just a problem seeing all these geometry spaces. So seeing the field, the gauge geometry, and then the physical geometry, I just had a hard time seeing the map between the two, but it's a quotient. That's why it's hard to.
Yeah.
Brilliant. Okay, thank you.
Yeah, Cartan was the sharp guy.
Oh my God, it's so cool. Whoa.
Yeah. Okay. Well, I'm sure we'll talk more about this, Alex.
Absolutely. Thanks for your time, Professor.
Oh, you're welcome. This is fun. I'm glad you're interested in this. It's fun to share it with people who get it. All right.
I mean, I'm really glad that you're willing to show this to me. So thank you.
You bet. See you, Alex.
Okay, bye.